Hello everyone, welcome to today's presentation. I'm excited to introduce our topic, electromagnetic waves. On this first slide, we have the title, which sets the stage for what we're going to explore. Over the next few slides, we'll cover the basics of electromagnetic waves, how they travel, and why they are so important in our daily lives. So, let's dive in and learn more about this fascinating subject. Let's take a closer look at the Hertz experiment, which was a pivotal step in understanding electromagnetic waves. Heinrich Hertz conducted this experiment in the late 19th century, and it helped prove the existence of radio waves. By generating and detecting these waves in his laboratory, Hertz confirmed that electromagnetic radiation behaves as predicted by Maxwell's theories. This experiment not only demonstrated the wave nature of electromagnetic energy, but also laid the groundwork for modern wireless communication. Connecting this to the properties of electromagnetic waves, we see how their ability to travel through space without a medium is fundamental. Understanding these properties, including their spectrum, is key to grasping how different types of electromagnetic radiation, from radio waves to gamma rays, are all interconnected within the electromagnetic spectrum. Now, let's look at the velocity of electromagnetic waves in different media. In free space, the velocity is given by c, which equals 1 divided by the square root of the product of the permeability of free space and the permittivity of free space. This value is approximately 3 times 10 to the power of 8 meters per second. When electromagnetic waves travel through a material medium, their velocity is reduced, and it is calculated as 1 divided by the square root of the product of the medium's permeability and permittivity. Here, mu and epsilon represent the absolute permeability and permittivity of that specific medium. Moving on, variations in the electric and magnetic fields happen simultaneously, meaning they reach their maximum and minimum points at the same locations and times. The electric field, which we often call the light vector, and the magnetic field are always perpendicular to each other, as well as to the direction in which the wave propagates. This orthogonal relationship is fundamental to understanding electromagnetic waves. Furthermore, the amplitudes of these fields are related by the equation C equals the ratio of the electric field amplitude to the magnetic field amplitude. This relationship shows that the electric and magnetic fields are interconnected, with the speed of light linking their magnitudes. Finally, in regions free of charges and conduction currents, Faraday's and Ampere's laws take on a symmetrical form. These laws tell us that a changing electric field produces a magnetic field, and a changing magnetic field produces an electric field. This mutual generation is the core reason why electromagnetic waves can propagate through space without any material medium. The electric and magnetic fields are always perpendicular to each other and to the direction in which the wave travels, creating a dynamic, self-sustaining wave. When observing the sparks, it was most intense when the spheres S1, S2, and their primed counterparts S1, S2 were aligned parallel to each other. This clear pattern provided strong evidence of the polarization of electromagnetic waves. Hertz was able to generate these waves with a wavelength of nearly 6 meters. Then, 7 years later, J.C. Bose made a significant breakthrough by producing electromagnetic waves with wavelengths ranging from 25 millimeters down to 5 millimeters. These oscillating electric and magnetic fields are what we call electromagnetic waves. The waves are radiated outward from the spark gap, and during the experiment, the detector is positioned so that the magnetic field created by the oscillating current is perpendicular to the plane of the coil. This setup causes an electric field to be induced by the magnetic field, which then ionizes the air in the gap between the spheres. This ionization creates a conductive path, allowing current to flow across the gap, resulting in sparks. Because of the high voltage involved, the air in the tiny gap between the spheres becomes ionized, providing a discharge path for the plates. This leads to a spark passing between the spheres, and at the same time, charges on the plates oscillate at very high frequencies. This high-frequency oscillation produces a strong, oscillating electric field in the vertical gap between S1 and S2. In response, an oscillating magnetic field of the same frequency is generated in the horizontal plane, perpendicular to the gap between the spheres. In the setup, the copper or zinc plates are kept parallel and separated by about 60 centimeters. The metal spheres are mounted on metal rods, with a gap of roughly 2 to 3 centimeters, and an induction coil supplies a high voltage of several thousand volts. Together, these plates and the rods with the spheres form what we call an LC circuit, which is fundamental in generating and studying these electromagnetic waves. Now that we've explored the end of the electromagnetic waves section, let's move on to the electromagnetic spectrum. On this slide, we see a detailed table that categorizes different types of electromagnetic waves based on their wavelength, frequency, sources, and uses. Starting from the top, ultraviolet rays, or UV rays, have wavelengths ranging from about 3.8 times 10 to the minus 7 meters down to 6 times 10 to the minus 10 meters, and frequencies from 8 times 10 to the 14 Hz up to 3 times 10 to the 17 Hz. These rays are produced by atoms and molecules during electrical discharges and also come from the sun. They have important applications in medicine, sterilization, killing bacteria and germs in food, and even in forensic work like detecting invisible writing, forged documents, or fingerprints. Next, we have X-rays, which have even shorter wavelengths, from 10 to the minus 9 meters down to 6 times 10 to the minus 12 meters, and higher frequencies, reaching up to 5 times 10 to the 19 Hz. They originate from inner or tightly bound electrons and atoms. X-rays are widely used in medical imaging, such as X-ray photography, and in cancer treatments. They're also used to locate cracks in metals, detect smuggled goods, and analyze crystal structures. Moving further into the spectrum, gamma rays, or gamma rays, have wavelengths from about 10 to the minus 10 meters down to 10 to the minus 14 meters, with frequencies soaring from 3 times 10 to the 18 Hz up to 3 times 10 to the 22 Hz. These rays come from radioactive substances and are invaluable in studying nuclear structures and conducting astronomical research. Below these, we have the longer wavelength waves. Radio waves, which range from a few kilometers to 0.3 meters, are produced by oscillating electronic circuits and are primarily used in radio and TV broadcasting. Microwaves, with wavelengths from 0.3 meters down to 1,000th of a meter, are used in radar, studying atomic and molecular structures, and microwave ovens. Infrared waves, with wavelengths from 1,000th of a millimeter up to about 7.8 times 10 to the minus 7 meters, are emitted by molecules and hot bodies, and find applications in industry, medicine, astronomy, night vision devices, and even in revealing secret writings or ancient wall paintings. Finally, we come to the visible spectrum, which is the range of light our eyes can detect. Its wavelengths span from about 7.8 times 10 to the minus 7 meters to 3.8 times 10 to the minus 7 meters, with frequencies between 4 times 10 to the 14 Hz and 8 times 10 to the 14 Hz. This range is produced when electrons in atoms and molecules are excited, and it's essential for optics, vision, and photography. In summary, the electromagnetic spectrum covers a vast range of waves, from very long radio waves to extremely short gamma rays, each with unique sources and important applications across various fields.